the first thing I want to look at is actually the back. Okay, so just fold it over. So what we're trying to do is create like a quick reference sheet for you. So the back is going to be the general idea of how all graphing with transformation works. And then the doors are going to remind you what our parent functions are and that you can perform these transformations on each of those different types of functions. Okay? So on the back, for the title, transformations will do because it's going to summarize all of them for you. And when we think about a function, just to give you an example, so up here next to this title, if you had y equals or f of x equals, and you have some type of function, so it could be absolute value bars, it could be the greatest integer function brackets, it could be quadratic starting this unit, it could be a square root. All of those have like the function symbol that tells you you're taking square root or you're taking absolute value or you're doing the greatest integer function. Let's say I use that one as an example. Okay? Those brackets exist. And then there's changes that are occurring inside the bracket, so within the function, and then outside of the function. Okay? So your x was in your parent function. It was inside the function. But I'm going to make a couple of notes here about how things change. Color-coded a little bit. So the stuff that could have happened inside the function is that something could be subtracted from x. Okay, and what did you guys see in the absolute value investigation we did? If you had like x minus 2 inside the absolute value bars, where did that shift your graph compared to the parent function? Horizontally, and 2 to the right specifically if it said plus 2, 2 to the left, right? There could also be a number in here multiplying, which could be negative or positive and could be any value, and we'll talk about what that will do. Those are all inside of the function. So do you guys understand what I mean inside the function? These are all things that happen to x before you perform the function that this is about. So before you do the brackets, these things are all happening to x. Before you do the absolute value bars, these things are all happening to x. Okay? Before you do the square root or the squaring, all these things are happening to x. They're inside of the bracket affecting x. If you did the order of operations, you would do these things before you ever performed your function. Okay? The stuff that I'm going to refer to as outside of the function is stuff that you would still do to get your final calculation, but you would do it after you've performed the absolute value or the greatest integer brackets or after you've taken square roots or squared something. Okay? So again, there could be something added on to the end. And what did we see with our absolute value functions when we did like plus k? If we put plus 5 at the end of the absolute value function, what was that going to do to our parent function? Good, a vertical shift and move it up 5, right? And then there could be a number multiplying out here as well. And again, it could be positive, it could be negative, and then the value of the number will matter as well. So like you guys said, the h was a horizontal shift and the k was a vertical shift. And that trend continues. Everything that's happening to x before you perform the function is causing a horizontal change in the graph that you see. So it's taking the parent function and doing something to it horizontally. So, yeah? It's not going to be the slope. We'll talk about exactly what it is. Different graphs look different ways, so slope is kind of, maybe it ends up being that in some things, you know, but we wouldn't exactly refer to it as that. And then this stuff that I put in green, the stuff that's on the outside, is going to make any vertical changes to the graph. So our goal in knowing this is this. We're going to learn some functions, and they're going to get complicated, like the greatest integer function did, right? Once we put all those numbers in there, just making an XY chart and plugging in random stuff is helpful, but it doesn't always get you the graph because you don't know exactly where all the endpoints are and stuff like that. So knowing how far apart the steps were, how long they were, and all of those things is what made it easier for us to get our graph. This is going to tell us that, but not just for greatest integer function, for every function that we learn. So we're going to learn the most basic parent one, and then as long as someone writes this for us in this style, We can take the parent graph and just do these things to it and have the new graph without ever plugging in a number. Okay? That's the idea behind it. So we're going to split our transformations up into different categories. So the first category is going to be translations. So we're just going to list them downward. So I'll show you guys how I did mine. Those of you that are like worried about space and stuff, you'll have, I think, plenty of space. So there's like 4 different categories, and then next to each one we have a little example. So it's kind of like a 2-column, but this column doesn't need to be as big over here. Okay, and like space for 4 of them on the way down if you're worried. All right. So first one is translations. Think about geometry. What kind of transformation is a translation? What are you doing to the object? Yeah, Brooke? Good. Putting it somewhere else, okay? And by what kind of action? Yeah, just basically like pushing it, right? So that means we can push to anywhere on the graph, and basically we're going to know where to go based on our H's and our K's, right? Our left, rights, and our up, down. So we're not flipping the graph. We're not pulling it, stretching it, compressing it. We're keeping the exact same shape. We're not flipping it around. We're just moving it left, right, or up, down, okay? Like those little puzzles where you have to slide things in and out of stuff, right? Okay, so translations are basically shifting. So they can happen in both vertical and horizontal. What controlled our horizontal shifting? H, okay? So it happened within the function. So in function notation, if you didn't have a whole function written out, you would see something like this, okay? Basically that the H is affecting the X within the function. It's not happening beyond the function, okay? And this is causing horizontal shifts. Okay. Or horizontal translations, which basically means you're moving left and right. And you could see a plus or a minus. I'll just write plus or minus for now. But you guys know how the formula works. It says minus H, so if you see minus 2, the H is actually the positive 2, okay? So if we want to do a vertical shift, we need to add K on. It needs to be after you're doing the basic function. So how that they would note that in function notation is like, well, you're going to do the function, like the absolute value bars or the greatest integer bars or whatever it is. And then after it, you're going to add or subtract on this special number, okay? And that represents our vertical shifting, so like up and down. So an example next to this, if you had a parent function where you have f of x equals x squared, so we'll see this a lot in the unit that we're studying right now. If x squared is our parent function, then in order to get a horizontal shift, we would want to see something being added or subtracted to the x within the function. So an example would be if your function changed from x squared to like x minus 2 squared. Okay? So x squared was the parent. X minus 2 squared has a horizontal change. Do you guys see why it's a horizontal change? That the adding or subtracting of 2 is happening inside of the squaring, and it's happening to x. Okay? Where would this move your graph? So you'd have the parent. If somebody decided to put a minus 2 in here, where is it going to move your graph? Think about how h works. 2 to the right. Okay, so that's going to shift our graph 2 to the right. If we wanted a vertical change, rather than having put the minus 2 of the squaring, we would have still had the x squared, and after the squaring was done, we would have then subtracted 2. What kind of change is this going to cause? A shift down 2. Okay? So, how it's noted in function notation when people are talking about it generically, you have this kind of business. How you're going to see it come to life in a problem is you're going to have a function that you know how to work with, and you're going to see these numbers show up in these places of the function. Good? Okay. So it can happen with any of them. That's the cool part. You have to learn how to do these, but you can do these same transformations over and over again with every parent function. All right, the next transformation that we're going to look at is a reflection. So thinking about geometry and what you guys studied there, what would you expect to see when something is reflected? Huh? Good. Okay, so it's like folding the paper in half and getting the mirror image on the other side, right? So this is kind of like a flip. Okay. But we're going to use the term reflection. Again, what I'm trying to give you guys is the correct terminology, translation, reflection, and something for you to relate it to. Okay? So a flip or like a mirror image. Now, on our graph, there are two axes that we can use as our mirrors or the places that we're flipping over. Okay? The x-axis and the y-axis. Okay? Where did you guys see, how did the reflections happen? So like when you saw the absolute value v, what got it to flip upside down instead of open up? What had to be in the equation to make it open downward instead of opening upward? Samantha? Good. In absolute value, we saw the negative number outside of the absolute value bars, right? So was that a vertical or a horizontal thing happening? A vertical thing. It was happening out here. So that's a vertical thing because it was going from up and then all of a sudden it was facing down. That's a vertical change. From up to down is a vertical change, right? But what axis would you be flipping over while you're doing that vertical change from up to down? The x-axis. So it's kind of weird because you guys don't always like that. This is what I found because the x-axis goes like this, right? So when you think of flipping over the x-axis, you tend to not think vertical, but you need a horizontal thing if you want to flip something from up to down. It's got to cross over this line, okay? So things that we call vertical reflections could also be said as reflecting over the x-axis. Okay? And like you guys said, that's when we saw a negative show up out here, outside. And that makes sense because the outside stuff is causing the vertical changes. Okay? So if we wanted to have a horizontal reflection where we wanted something to shift from like the left side of the graph to the right side of the graph, how would we make that happen? Savannah? Okay, good. So we would call it flipping over the y-axis or a horizontal reflection. And what do you think would have to show up in your equation for you to know that you can do that? Brooke? Good. So the negative would then be here on the inside because it's causing a horizontal change or a horizontal reflection. Okay, does that make sense to everybody? So for reflections, we're thinking negatives. That's what's showing up in our equation. When the negative is showing up, and it's affecting the x before you perform the function, this is a horizontal reflection. But a horizontal reflection means you're flipping over which axis? So think about flipping a book page horizontally. So you're going from left to right or from the right side to the left side. So that's a horizontal reflection. What are you flipping over? The y-axis, okay? And the reason we need to know both, the horizontal-vertical connection helps us because it's kind of like, oh, all this stuff is horizontal, all this stuff is vertical. But then you're going to read things a lot that say a reflection over the y-axis, a reflection over the x-axis, and you've got to understand what that looks like, okay? So if we want to see a vertical reflection, our negative is going to be after the application of the function. So it's outside of the bars or the brackets or the squaring, okay? Or the radical, whatever is there. This is going to cause a vertical reflection, okay, which we talked about would reflect over the x-axis. And I'll be out of your way. How come with absolute value functions, we didn't see any of these horizontal reflections? Yeah. Yeah. So with the absolute value bars, if I horizontally reflect it over the y-axis, doesn't look really any different once you're done, right? Because the y-axis was like the axis of symmetry, and that's because of the properties of absolute value, where if you like did have a negative in there with x and you factored it out, by the time you got the negative 1 by itself in absolute value bars, it just looks like a positive 1, right? And it's done. And that's why we were able to factor things out of absolute value bars, and then we kind of weren't with greatest integer function, because they have slightly different properties in that area. Okay? So any questions about translations or reflections? Okay, so an example of your reflections. Let's say you were given a parent function a square root. Okay. Then an example of a horizontally reflected graph, okay, would be that you still have your square root with x, but there's a negative applying x inside the square root. So some of you might be freaking out and be like, oh, you can't take square root of a negative. Well, I can plug in whatever I want for x here, right? So what if I plug in -4? Then the negative makes it +4, and can I take the square root? Yes, I can. Okay? So what's happening, and we'll look at this graph in a little while, is this graph has some different restrictions because of the way you calculate square root. But it does form a picture on the graph, and this negative being here flips that from left to right. Okay? If I want a vertical reflection for the square root of x, I would have my square root of x, and I would have my negative on the outside of the function. So that will take care of all of my changes. All right, so are we good with translation and reflection? Okay, and those ones are very related to absolute value, where we got to do most of the stuff, so they make sense. The next two things are the more difficult things. So next we're going to talk about compressions and stretches. But rather than split it up compressions and stretches, we're going to split it up horizontal and vertical. Yeah. Sit in. No? All right. So I need a blank page. All right. So let's talk about vertical first. So the next category is going to say vertical stretch and compression. So a vertical stretch or compression is like I take your parent function drawing on the graph, and I literally grab the top and bottom of the graph if your paper was flexible, and I just stretch it, or I take it and I compress it. Okay? So let's think about the greatest integer function, because this is where you guys saw it. So you had your steps, right? If I took your parent function and I stretched it vertically, what's the change you're going to see with your steps? Yeah, you would see them get further apart, right? But am I changing the length of the step horizontally or any of that by stretching it vertically? No. If I compress it vertically, you're going to see the steps get closer together, right? That's how it's going to look, okay? So those words stretch and compression, you can visualize that way. Now, both of these things come from the same part of the graph. This is vertical, so I'm looking for something outside. These depend on that a value that was outside of your function. Okay, so they depend on this number right here. Now, we already know if a is negative, we're not discussing that here as a stretch or a compression. If a is negative, we'll talk about a reflection separately. Okay, so here we're only going to talk about the number part of a. I don't care if it's negative or positive, because if it's negative, that's a reflection. I do that separate. Does everybody understand? So we're just talking about the number part. Okay, so think about the greatest integer function. When you looked at the number that was outside the brackets that was going to control whether things were stretched further apart or closer together. Okay? If I wanted my steps to be further than 1 unit apart, what kind of number had to be right here for a? Okay? A fraction. It could be a fraction if it's a certain type, but it didn't have to be. If I wanted my steps to be more than 1 unit apart, what type of number had to be here? Nothing? It could be an integer. So it could be a fraction, it could be an integer, either one of those. But what about it is going to guarantee more than 1 unit apart? Lauren? It could be a whole number. It doesn't have to be. A positive number? The positive part's not going to control it, because all the negative's going to do is a reflection. So it doesn't have to be positive to make the steps get further apart. What had to be true about that number, Alvin? Okay, so if the number's 1 itself, you're getting exactly like what our parent function looked like, right? Steps that are a unit apart. If the number's more than 1, one thing will happen. If it's less than 1, something else will happen. If we put a 2 right here in front of our greatest integer brackets, what happened to the vertical distance between our steps? They became 2, right? So basically, if the number here was bigger than 1, it vertically stretched out our graph, and our steps got further than 1 unit apart, okay? So I don't care whether it's positive or negative, because the negative is addressed in the reflections, which is why I'm using absolute value bars here. If the number part of A is bigger than 1, then I have a vertical stretch. And again, we saw that with the greatest integer function. However, if it's smaller than 1, like if it's 1/2, my steps are then only half a unit apart. It's like someone took the paper and squished the steps closer together vertically. That is a vertical compression. Is this okay with everybody? So this is basically whatever you used to have. Like in my parent function, they were 1 apart. If you put a 2 here, I say they used to be 1. It's getting multiplied by 2. 1 times 2 is 2. My steps will now be 2 units apart. If it's a 1/2, I say, well, it used to be 1. Now it says 1/2. 1/2 times 1 is a half. My steps are now half a unit apart. Is that okay with everybody? So it's changing how far apart points are on our graph, but only vertically. It's not doing anything to them horizontally, only vertically. And if it's 2, you times it by 2, and they get stretched further apart. And if it's 1/2, you times them by 1/2, and they get pushed closer together vertically. Okay? So like we said, we could see this in our greatest integer function. Okay? And we could see a vertical stretch as if the 2 was like out there, and a vertical compression if there was something like 1/2. So there are also horizontal stretches and compressions. You guys saw this in the absolute value function and in the greatest integer function. One number controlled how far apart our steps were vertically. A different number controlled whether our steps got longer or shorter from the parent function horizontally. Okay? So we knew that our parent function started with steps that were 1 unit long. And then depending on certain numbers showing up in our problem, either those steps got horizontally stretched, so they were like 2 units long, or they got horizontally compressed, so maybe they're like a half or a third of a unit long. Okay? So the horizontal, I already have this. Can I go to another page so people don't struggle to see on the lower part of the board? So we also have horizontal stretches and compressions. And again, where did you see the number show up in the greatest integer problem where you went, oh, that means I have to make my steps longer than 1 or shorter than 1 or something like that? Savannah? Good. As the b value, kind of inside the brackets with x, right? In absolute value, we kind of ignored that because there was always a way for us to get it out. But that's not going to be true in most of the functions. They're going to work more like greatest integer function. So what we focused on here is we saw this number show up inside the function multiplying x. And then we always factored it out so we could see our true h value and what that was. Okay? So again, if b is 1, you just have your parent function, and they don't write another number there. But it's going to fall into 2 categories. What about when b, and again, I'm using absolute value bars because I don't care about the negative part. We discussed that when we discussed reflections. Right now, I care about the number part of the b value. Okay? What about when it's bigger than 1 versus if it's less than 1? And before we assign exactly what these are, I want you to think again about what you saw with the greatest integer function and how it operated. If you had that parent function again, and we say that b is greater than 1, that's like putting something like the number 2 inside of the brackets multiplying x. We say is b is less than 1, that's like putting 1/2 inside multiplying x. Okay. When we saw the number 2 inside multiplying x for our greatest integer function, we knew that affected the horizontal length of our step, which is now why we see it falling under this horizontal stretch and compression category. How did it affect the length of your step? When 2 was the number that showed up in the equation, how long did our steps end up being? Hannah? No. I know. The horizontal stuff is so tricky. Good. Half a unit, right? Horizontal stuff is crazy, right? K is all nice. It says +1. You go up 1. H says x minus 2. You don't go minus 2. You actually go +2, right? Same thing on the outside. It's like, oh, there's a 2 on the outside. The steps are 2 units apart. Yay, it's so nice. You do exactly what it says. Then you get on the inside of the function, right? It says 2. No, you don't actually multiply it by 2. You actually multiply it by 1/2. Okay? So your steps used to be a unit long, and now they're only half a unit long. And it all has to do with the way we plug numbers into the function, like we saw as we plugged in those values for the greatest integer function. So when b is bigger than 1, so this number is something greater than 1, you actually have a horizontal what? Compression, right? Hi. Okay. And then when b is less than 1, you actually have what? Yeah, stretch, okay? Which means when we're doing calculations later, basically like in these ones, to get the step length, you took your original step length 1 and you multiplied it by the reciprocal, right? Like 1 over b, okay? This is like the original distance between the points, and notice you're multiplying by the reciprocal to get the new distance. So if it said 2, I say, they used to be 1 unit long, but 1 multiplied by the reciprocal of 2, so 1 times 1/2 is giving me the half a unit long steps. Okay? It says 1/2. They used to be a unit long. I don't take a unit times 1/2. I take a unit times 2 over 1 or 2, and I get 2 unit long steps. Okay? Whereas, again, the vertical stuff is like much simpler. Okay? Someone puts a 2 out of front, you say, my step length used to be 1. I'm going to literally multiply them by 2 because it says 2, right? So you still take your original distance between the steps, and you just multiply it by a. Okay? So vertical stuff, a lot easier to deal with. Horizontal stuff, a little bit trickier. But these transformations are going to hold true for all of our different functions. Okay? Is that good with everybody? We know where we're at? Okay. So your homework tonight is going to be about this stuff. Okay? So there's going to be like a picture, say, I don't know, with some points. And they're going to call this like f of x. Okay? Oh, there it is. It's on a graph or something. Okay? And then they might ask you, like, okay, what is f of x minus 3? And then you have to redraw the picture. What are you going to do to the graph to show this transformation? So look at this transformation. What kind of transformation is it? It's horizontal. Is it stretch compression, reflection, or translation? Translation. Which direction? Right 3. So if they ask me to describe it, the horizontal translation, right 3. If they ask me to show them on the graph, I'm going to take everything and move it to the right 3. Okay? So you're going to be applying this idea to graphs, to equations, and stuff like that, but you should have the general idea with all of the different transformations. Does everybody understand? Okay, so homework number 1 is tonight's homework. It's going to be all about transformations represented in different ways. Tomorrow's a minimum day. We will not have time to go over it, but on Thursday we will have time to go over both homework 1 and homework 2. Okay? Makes sense to everybody? So you know where we're going with this? All right. So you guys can leave the transformation book for now. I know we got to put some other stuff in it, but it's fine. So use those notes to help you with tonight's homework. Okay? And then what I want to do now is if you have the Unit 2 note guide. All right, super important. The place where any graph crosses the x-axis is called the x-intercepts, right? So you guys tend to be okay with if I give you a graph and say find the x-intercepts, you know what I'm talking about. But if I just give you an equation and I say solve for the x-intercepts, you're like, I don't know, Miss Dahl, what you're talking about. X-intercepts are the same thing as roots, are the same things as zeros, are the same things as these solutions to the equation. So whether somebody calls them any of those things, you should be familiar enough with that word or have it connected to another word in your head that you do know what to do when someone says that you know what they're asking for. Does that make sense to everybody? So those things where you plug 0 in for y and you find x or you solve the equation, those things are all those different names right there. Zeros, solutions, roots, and x-intercepts. So no matter how someone phrases a question, we better understand what those things mean. Okay? The other important parts of the parabola that we want to be able to find while graphing, we want to be able to find the axis of symmetry and my very slow-moving vertex. Okay? It's really slow every time. Okay? All right, are we good with this? So this is the structure of the parabola, the things we want to know how to do. The axis of symmetry and the vertex are going to show up a lot graphically. These solutions are going to show up both graphically and also when we don't graph and we just want to be able to solve the equation in that form. All right, so first form that they're going to give us the equation in, standard form. How many of you guys have dealt with this? So people give you like 3x squared plus 2x plus 1 or something. Yeah. Okay. So what are some options for solving this, for finding those x-intercepts or solutions or roots? What are some different ways you already learned in previous math classes to solve quadratic equations when they're in this form? Okay, so if it's factorable, we could factor it, right? What if it's not factorable? Oh, so the cover-up method will find intercepts for linear things, but it's a little bit harder here. It's easy to find the y-intercept, but to find the x-intercept, you would then have to go and do the factoring, or some other options if it's not factorable. Michelle? Oh, the quadratic formula. What a beast, right? How many people know I have the quadratic formula memorized? Okay, and be honest with me. How many of you are like, oh, quadratic formula, I remember it was something really important, but I cannot remember it. Okay, let's start remembering it. It's in your book. Go and find it. Okay, sing the song every night or the little poem or the story or whatever it is you did to remember. Okay, like there was a rad boy, something like this, right, that we do. It's all fun. Okay, so let's say that we did use quadratic formula to solve it. Here's a little, this is what the quadratic formula looks like, right? But I broke it into its two parts. Normally you don't write them separately. You just write one of them and you put plus or minus. But that gives you two solutions, right? One with the plus and one with the minus. Okay? So all I did was break them apart. I'm not saying these actually ended up here. Okay? We're just being kind of generic. But I know that the plus one would be on the bigger side of the x-axis and the minus one would be on the smaller side. Does anybody remember how to find the vertex? All right, so let's talk axis of symmetry. If these are your two roots, because a parabola has this beautiful symmetrical thing going on, right? If these are the two roots, they happen the same distance from the middle of the parabola, right? Where the axis of symmetry would be. If you have two numbers on a number line and you want to find out exactly what's in between them, what would you do? Jordan? Add them up and divide by 2 because you would average them and you'd find the middle between them, right? Okay, so that's what we're going to do right here. We're going to average these. You guys don't have to do the work. I'll do the work. Okay? I like it. All right, so when you add these up, they already have common denominators, so that's nice. Okay, the denominator is 2a. And then when you add the numerators together, what do you get? So if you add this numerator with this numerator, you get negative 2b. All that ugly radical stuff cancels out because one's negative and one's positive, okay? All right. So I get negative 2b over 2a. The 2's will cancel, so I have negative b over a. So that's adding them together, but then I need to divide that by 2, right? Would you guys agree with me that dividing by 2 is the same thing as multiplying by 1/2? Yes. Okay, how many of you guys have seen this formula before? Yes. Okay, so you probably had it unattached to anything. Well, here's where it really came from. If the quadratic formula can find you those two solutions, then the average of those two solutions should find you the x that's in the middle of them. When you average the quadratic formula, you get this. So that formula wasn't just like somebody said, you know what, I'm going to say that you do this to find the vertex. Like, no. This all stems from like some basic stuff. But then as people did it over and over again, they're like, hey, if I just tell people use this formula, it does all the steps in one. So let's just do that. Okay? So that's where our negative b over 2a comes from. Now that gets you the axis of symmetry. So you know the x coordinate of the middle. But if you want to graph the vertex of your parabola, if I want this location, I need an x and a y that goes with it, right? What do I do once I have an x and I want the y that goes with it for a specific equation? Okay? I can plug the x back into the formula. So you guys are probably going to hate the notation. Okay? Negative b over 2a is my x value, right? That's whatever that is. If it comes out to be 5, it's 5, whatever. And what does this mean that I wrote in the y coordinate spot? Savannah? Yeah, so the x is negative b over 2a, but I want you to go plug it into f, and you'll find the y that goes with it, right? Okay, so the notation is ugly because you guys don't like all these variables and stuff like that. But if we're being generic and not giving you a single example and trying to give you an overview, okay, you can always find the x coordinate when it's in standard form using this formula of x equals negative b over 2a. If you want to know the y coordinate that goes with it for the vertex, you have to plug it in. If this is, you're going to look back on your notes and be like, I don't know what that is, right? Plug in the x coordinate to find the y coordinate, right? Very simple, okay? Are we good? So we're just building relationships right now. Oh, I learned this in Algebra 1. Oh, it actually connects to something graphical. It wasn't this entirely separate thing I just memorized and then plugged things into, okay? That's what we want in Algebra 2, connections. All right, they might not give it to you in standard form. They might give it to you in intercept form. So this comes down to if it was factorable, right? If it was factorable, maybe they've already factored it for you, okay? So P and Q is just whatever numbers ended up in there when I factored. A came out there just like the AX and the AX squared bx+c thing. Okay, how do you think you find the x-intercepts if you already have it factored? So if somebody walks up to you and says, hey, I've already done all this work. I'm in Algebra 1. Okay, I don't understand how any of this works, but I know I can do these procedures. Okay, and they give you this like 0 equals 3 times x minus 2 times x plus 5. What would you be able to tell them about the x-intercepts on their graph? Jason? Good. You can just set each factor equal to 0 then, right? This zero product property, if you want this multiplication problem to end up being 0, then one of these factors must equal 0, right? Because 0 times stuff is the only one that's 0. So you try each one and say, oh, well, x could equal 2 or x could equal negative 5. Okay? And that's how they come up with these points. So if it's x minus p times x minus q, when you set x minus p equal to 0, x will equal p, whatever number that is. And when you set x minus q equal to 0, x will equal q, whatever number that is. Yes? Well, the 3 doesn't get set equal to 0 because it's not 0. It's a specific value. We only set equal to 0 when solving the things that have x in them because 3 is already determined to be 3, unchangeable. X plus 2 and x minus 5 or x minus 2 and x plus 5, we can change the values of those dependent on x. Okay? So my point in putting p and q here is just like solve for your factors, right? You figure out the x's. P's and q's, who cares what I call them, right? You get the numbers from your factor. In this problem, 2 and negative 5, whatever. Okay? So if it was factored for you, this would be a really quick way to graph, right? Get those numbers where it crosses the x-axis. Again, if you have the places where it crosses the x-axis, how are you going to find the axis of symmetry? Okay, so if it was written in standard form, negative b over 2a, but now we don't have a's, b's, and c's all in the right place that they go. But what could we do here if we have this number and we're trying to find the center? What are you going to do there? Just average them again, okay? You got the solutions differently this time, but you could still just average them. Yeah. So we're going to p plus q. This is not a formula you need to memorize. Have you ever seen this formula before? No. But what I want you to think in your head is, oh, if I have factors, can I quickly get some information that I could put on a graph? I sure can. I can get the x-intercepts. And then I want you to recognize, if you have the x-intercepts, are you stuck? Like, oh, I don't know anything else. No. Somewhere in between them is exactly where your axis of symmetry is, right? So go find that special number. So right now I had to write it like that because I'm using p's and q's. But that's not a formula you have to memorize. I just want you guys to recognize when you know that about the graph, you have something else you can go find. You can go find the number in between them, okay? And what did we say? Once you found the x value in between them, how would you get the vertex point? Plug back in the x value. And again, you're going to hate the notation, right? Because I have all this generic stuff going on. Is my point for you to memorize weird notation? No. Is my point for you to remember how the quadratic works? And some vocabulary and some things associated with it and how you're going to find things with algebra that relate to things on the graph. That's what I want you to look at, okay? So again, you would then take that, you'd average it, you have your x value, you plug it in to find your y value. You don't like this? Fine. Find the number in between by averaging. Plug in the x to get the y. There's different ways to summarize it. I just want you to realize all these things you learned in Algebra 1, setting these equal to 0 and solving them, aren't just giving you random solutions over here to x equals. They're totally related to your graph, and you need to connect all that information together while we're working on this unit if you want to be able to do everything we're going to do. Okay? All right. Last form that they could give it to you in. Vertex form. Why do you guys think they call this vertex form? It automatically finds the vertex. Where do we get our vertex from? H and K. This looks just like the absolute value function, but with squared parentheses instead of absolute value bars, right? And then we just talked about transformations. This is set up just like a transformation problem, only what kind of transformation is not here? B, and B was representing what for us? Horizontal stretches and compressions. Could someone put a B in the equation? Yeah. Okay, would it be considered vertex form anymore? No. Okay, in vertex form, we don't have to look at any number that's a horizontal stretch or compression. Someone's done us a favor, and they've rewritten the equation in an even simpler form where we get to ignore horizontally stretching and compressing. Okay? So like you guys said, the reason this is called vertex form is you have your H and K right there. So if someone's giving me the equation in this form, what's probably the first piece of information I could put on my graph? The vertex. Okay? So that's what I would want to do first. There it comes, really slowly. Okay, so here's my HK. If I know where my vertex is, what else do I know? My axis of symmetry, because it's going to be a vertical line going through this vertex. What's the equation for the axis of symmetry going to be if my vertex is at H, comma, K? I see Lauren and I see Savannah. They've answered so many questions. Yes, Andrew. So, not A, because it has to cross through here. So it's got to be a vertical line that crosses through here. What are the equations of vertical lines? How do they start? X equals, and then you have to say which number they're crossing through. So this is going to cross through here. We're not going to call it 3 because we don't know how the graph is scaled. But we know that here is lined up with here. So which x value must that be? Look at the point. H, right? Okay. Remember on our last test how you guys wrote down the vertex for the absolute value function? And then you wrote the axis of symmetry? Most of you were able to identify that the x-coordinate was just going to be the value in your axis of symmetry. What we weren't good at, and small note, you do need to say x equals that number. The number is nothing on the graph. Okay? It's not a point. It's not a line. It's not in anything. And later on, we're going to have things that have axis of symmetry the other way and a directrix going this way. So if you don't label x equals and y equals, I don't know that you know which way things are going. So in the future, you will get marked off points if you don't label your equations of lines with x equals and y equals. Not because I'm just crazy and don't want you to get the points, but for two reasons. It's not mathematically correct, and eventually I'm not going to know what you're talking about. And two, when you get to pre-calc honors, they're just going to be like, nope, nothing at all. You get no points for that. Okay, you got to label everything right because, again, they're not going to know what you're talking about. So our axis of symmetry should go through here and would be labeled as x equals h. Okay. And then I didn't really talk about finding the intercepts here. You would have to find points on the side. If you have these middle points, what's an old school way that you could get some points surrounding it if you needed to finish your parabola? Yeah? Yeah, just like pick an x, plug it in, plot it, right? If you do it on one side, you get to just mirror it on the other side. You can draw your parabola, okay? Or you can find the solutions. How to find them with this? You can't just plug into the quadratic formula, so I didn't really write anything about it. We're going to find several ways that you could quickly solve an equation in this form. But so I just generically labeled those again, like you would go find solutions if you need to. If somebody doesn't ask me for the solutions, I don't have to go find those ones. I can plug in any point I want. Okay? All right, so your homework tonight, guys, is homework